Let's talk about what a geometric mean is and how we can use it to help us find the lengths of segments in a diagram like what you see on the screen now, a right triangle with an altitude drawn in it. But first let's review from our previous video what happens when we draw an altitude in a right triangle. An altitude is a segment that connects a vertex of a triangle to the opposite side so that the altitude and the opposite side are perpendicular. And if you draw an altitude in a right triangle, it creates three similar triangles. So in the diagram we see here, segment RS is an altitude of triangle PQR because it connects vertex R to side PQ so that RS is perpendicular to PQ. When we draw this segment, it creates three similar triangles. The original full triangle is similar to this medium-sized triangle, which is also similar to this little baby triangle. And we learned in the previous lesson that we can use proportions and the Pythagorean theorem to calculate missing segment lengths in a diagram that looks like this. But the diagram I'm going to have you look at today is going to require a little bit of a different solving method. It's going to require you to use something called a geometric mean. The geometric mean of two numbers, a and b, is x such that a over x is equal to x over b. Geometric means have applications outside of right triangles and altitudes, but for our purposes today, what we're going to use it for is the fact that if an altitude is drawn in a right triangle, then the hypotenuse gets divided into two segments by the altitude. The altitude is equal to the geometric mean of the lengths of the two segments on that hypotenuse. So A and B are the sections of the hypotenuse, and x is going to be the altitude. Let's take a look at an example where we would have to use a geometric mean to solve. Here I have a right triangle with an altitude drawn in it, and the only information I have is the length of the hypotenuse split into two different segments. And our goal is to calculate the length of the altitude. So I'm going to call that altitude x, and I'm going to call the two segments on the hypotenuse A and B. It doesn't matter which one you call A and which one you call B. And I'll fill those numbers into the geometric mean formula. A over x equals x over b. So that turns into 2025 over x equals x over 784. When I cross multiply and solve, I get x squared equals 1,587,600. So how am I going to solve for x if it's x squared? Well, to get rid of a square, to get rid of an exponent like that, you have to square root both sides. So I find out that x equals 1,260 millimeters. So why do we have to solve this way? Well, let's take a look at what we would have done based on what we learned in the previous lesson. I taught you that every time you see a diagram like this, you should redraw it as three separate diagrams. One for the big triangle, one for the medium-sized triangle, and one for the little triangle. The big one's the easiest one to draw because you just copy and paste the original image but without the altitude in it. And let's go ahead and add these two numbers together to get the length of the entire hypotenuse, which is 2809. Now I'm going to draw two more triangles in the same orientation, one a little bit smaller and one a little bit smaller than that. These three triangles are in the same orientation because they all have their right angle in the top left-hand corner, they all have their short leg on top, their long leg on the left, and their hypotenuse goes up and to the right. Remember that we discussed in the previous video that by drawing these three triangles in the same orientation, it makes them much easier to deal with and set up proportions. So let's label our two new triangles, starting with the medium triangle, which is right here in the original diagram. I always start by labeling the right angle because that's the easiest angle to find. The right angle in the medium diagram is M, so I'll label this right angle with M as well. Then if I go along the short leg of my medium triangle, it ends at L. So I'll label this point as L. And then if I go from M along the long leg of the medium triangle, it ends at K. So I'll label this with K. And I can also label side KM as 2025. Now let's do the same thing for the little triangle. Again, the right angle is called M. This time if I go along the short leg, it ends at J. And if I go along the long leg, it ends at L. And I can label segment JM with 784. So these are our three triangles from the original diagram drawn in the same orientation. And if I asked you to find the length of the altitude, find the length of LM, well, let's go find LM. I don't see it anywhere on the big red triangle, but I do see it on the blue triangle and on the yellow triangle. Both the blue and the yellow triangles, the medium and the small triangles, only have one side length labeled, so I can't use the Pythagorean theorem to calculate LM. Instead, I would have to set up a proportion. But I don't have two corresponding sides that I know both lengths of. So it might feel like this is impossible to solve. But it's not, it's actually possible. Let's take a look at the proportion that we could set up using the two sides that I do know something about. I know the length of this long leg, so I'll write 20/25, and I'll put that over the corresponding length on the other triangle, which is LM. So that's long leg over long leg. And I'll set that equal to, well, let's see, I know the short leg of the yellow triangle, so let's stay in the same order. Let's do LM on top, because we have to say blue on top and yellow on bottom, and put 784 on the bottom. So that's short leg over short leg. So what we've written here is actually the same thing that we wrote for the geometric mean. Instead of x, we have LM, but it's the same idea. Cross multiply and solve, you would have to square root that 1 million and something number, and we get to the same answer of 1260. So this problem really isn't that much different than the problems that we did in the previous video. It's just you're going to have to use a rather creative proportion in order to solve, and it actually happens to be a geometric mean. Now that we know the length of the altitude is 1260, we can use that to calculate the lengths of LJ and LK just by using the Pythagorean theorem. For example, focusing on the little triangle up top, I know both of the legs, so I could calculate the length of the hypotenuse by doing leg squared plus leg squared equals hypotenuse squared. Simplify those numbers in a calculator, and I find out that the length of LJ is 1484. And we can do something similar to calculate the length of LK. In the medium-sized triangle, I know both of the legs, so I can calculate the length of the hypotenuse doing leg squared plus leg squared equals hypotenuse squared. Again, simplify all that in a calculator, and you get an answer of 2385. And that's all you need to know about altitudes and similar right triangles and geometric means. In our next lesson, we're going to be moving on to special right triangles, 30-60-90 triangles, and 45-45-90 triangles.